Thank you for the introduction. I'm Lai Zhou from Beijing Academy of Quantum Information Science. It's my honor to have the opportunity to make the presentation here. In this talk, I will show our ideal and system implementations to make the long-distance quantum key distribution simpler. And then begin my talk. Distributed quantum networks will lead to many great applications, such as quantum sensing, distributed quantum computing, and quantum key distribution. This picture shows a blueprint for integration of space-to-ground network. The quantum dots as a single quantum source, and there are many important components: quantum memory, single photon detector, and the quantum link, fiber or free space. The control system is very important here. For example, the phase stabilization for the single photon interference. I will emphasize this topic next. And polarization, calibration, and time synchronization being tracking for the free space link. There have been several trusted QKD networks in China and European and Tokyo. The next step should be untrusted QKD nodes based on the measurement independent device protocol and the entanglement QKD network. And our dream want to make it practical quantum repeaters. The following pictures show the field test of different networks. The first one is the QKD network. I think it's better to show this here. Yeah, the first one is the famous QKD network based on trusted nodes in China. The second one is the entanglement QKD. Okay, thank you. The second one is the entanglement QKD network, which is fully connected between 8 users. In such topological structure, the more shared users, the less key rate. This is their shortcomings. The third one is the entanglement swiping between 2 memories, but the longest distance is just 22 kilometers in the field trie and 50 kilometers in the lab. So I'm thinking about if we regard the current performance as the first generation, what is the second generation for the quantum communication? The network performance should be updated. Firstly, there should have high security. We need untrusted nodes. Secondly, covering long distance. For example, 300 kilometers to 600 kilometers for intercity communication. Thirdly, high rate, 1 kilobits per second for the voice communication in one-time part encryption, and 10 megabits per second for the video communication. And lastly is the miniaturization for the integration photonic chips. It's difficult to combine all the good characteristics together. So in this talk, we just focus on the first 2 characteristics marked on the red color, and the practical candidates is the twin-field QKD. I think most of people in this conference are familiar with this history of quantum distribution. The MDI QKD solves the problem of attack in detector, and the TF QKD extends the communication distance more than 500 kilometers. And there are so many achievements in recent years to improve the 2 key system performance, distance in fiber, and cycle key rate. Professor Liu Yang in Zhejiang Institute of Quantum Technology will introduce the 1000 quantum key distribution in the next talk. But my question is that could we make the system simpler so that it can be implemented in the future quantum network in a large area? Last month, there is a viewpoint report in physics to show the recent experiments to make the long-range quantum cryptography simpler. The new new results show that there is greater potential for QKD to become more practical. It's to be expected that there will be much progress on several points, including simpler, less expensive devices and more efficient protocols. I think there should be much cooperation between the experimental experts and the theory experts. We contribute two important papers here. Firstly, I will introduce locally generated flux corps to stabilize open channel for the TF-QKD. The second one, we make a measurement device independent QKD experiment with post-Marin Parry technique. So I will introduce that one by one. In 2008, the Toshiba research proposed the famous TF-QKD protocol. In TF-QKD protocol, Alice and Bob transmit identical optical fields to Charlie, who measures the interference of fields rather than that of individual photons, eliminating the need for photon coincidence. Several experiments of TF-QKD have shown that the key rate can overcome the rate loss linear bound. However, TF-QKD requires the field generated by the tube distance identical light source to be completely identical in every aspect, including the wavelength and the phase after propagation in the fiber. We can make a conclusion at this equation. There are two major factors that affect the result. The first is the delta mu, the frequency difference between the user's laser, and the second is the L, is the fiber length. So we should make much effort to make phase stabilization for the single photon interference. For the frequency difference, we can see this picture here. This black line is the interference result with just one laser, and the blue line is the interference result with two lasers, but the flux offset are almost zero. For the purple line and the green line, the frequency offset is minus 2 GHz and 2 GHz. So we can see that the interference result drift very fast when the flux offset is larger. The second factor is the fiber length. Usually, the phase drift rate is proportional to the square error. Several hundreds of kilometers fiber will contribute to a few kilohertz drift rate. Overcoming the above difficulties, there have been a lot of achievements to break the distance record one by one in recent years, including the Fairchild. For example, the 600 kilometers QKD and the 1000 kilometers, and the 511 kilometers, the failed try between Jilan and Qingdao in China. But the phase locking usually requires the dissimulation away, like this picture. The coma laser will have to share the frequency to Alice and Bob with the surface fiber. They will bring a lot of shortcomings. For example, one of the options is the optical phase loop lock technology to make the frequency between the common laser and the local laser to be the same. The setup are fiber resource efficiently and require additional frequency locking hardware and often optical amplify along the surface fiber because they are classical signal. In addition, the closed configuration is not friendly to their scalability into a larger network. As shown in this picture, we propose a simple configuration, the open twin field QKD. Alice and Bob locally generated their own optical frequency and their coherent sideband, which also know the coherent frequency comb. We generate the inactual optical frequency comb by passing the continuous wave laser through a force modulator, like this picture shows. their Fox meter is driven by the stable microwave source. And finally, we generate 13 Fox comb here, and with a spacing at 25 gigahertz. We choose 2 of them as the channel reference light for the fast tracking, and lambda Q for the quantum signal. The frequency in between is 100 gigahertz to make a good isolation between the 2 channels. The picture below shows the big picture of our system, and we can see. I will introduce that to you in details. Alice and Bob have a stable, ultra stable laser, and the new 9 waves is subhertz. Then the CW laser stabilizer will go to the phase modulator to generate the Fox comb, and the lambda Q will go through the encoder, recombine with the lambda C, and then lambda Q and lambda C will transmit in the same fiber. The Charlie will make an interference with the beam splitter. We get a high count rate with the detector C to make feedback on the phase modulator, and lambda 0, detector 0 and detector 1 will get the quantum signal of lambda Q. The whole system repetition rate is 1 gigahertz, but the effective clock rate for the quantum is just 500 megahertz, because half of them will be used for the slow drift rate compensation. This picture shows the result of phase stabilization with coherence frequency comb. The purple line is the free drift of the channel reference light, and the green line is the stabilized lambda C. The right diagram shows the auto calibration system. FPGA is here, get the feedback from the detector C, and make the feedback on the phase modulator on one pass. To lock the divisional phase to half pi between the channel reference light, the average count rate in detector is 13 megahertz, which is enough for the 200 kilohertz PID feedback rate. We transfer the interference result to the phase angle distribution in this picture. After enable the PID control, it's obvious to see that the phase has been stabilized to half pi, and the standard deviation are less than 0.1 radians. So this is a very great stabilized result. The yellow line here is the quantum signal after the faster phase control of reference light. Due to the coherence among the comb lines and the transmission in the same fiber, the phase instability of lambda Q is reduced as this equation. Currently, the drift rate is just 0.72 Hz drift rate. But there are also some residual drift rate because the lambda Q and lambda C's frequency is not the same, and there are maybe 10 meters not coexistence fiber in the encoder. I want to emphasize that the channel isolation is very important here, because if it's not good, there will be crosstalk between the reference light and the quantum light. We use 2 DWDM in the channel, and the isolation is more than 65 dB. In the following, I will also introduce the high count rate single photon detector fabricated in our group. It will be useful in the fast feedback. We will update the system maybe in the future, because the more count rate, there will be faster feedback rate. Our detector uses the ultra narrow interference circuit to improve the signal to noise ratio, and the gating rate is 1.25 gigahertz. In the high count rate, we can see that it can be reached 700 megahertz per second. It's a very high rate. And in the low noise, it can be, we multiply the repetition rate, and it may be less than 700 counts per second. It's also very good result for just APD, not the NSPD. More detectedly, there's a small APD can be fabricated in a small size. I think it's the same as our hand. So this detector will be very useful to make the system simpler and more practical in the future. The second important technology in our system is the fiber drift compensation technology. This picture shows maybe the theory diagram of the PTH locking for the ultra-stable laser. The cedar laser will locked to one transmit mode in this cavity with the PTH locking technology. And there is a EOM on the PTH locking path. So we can adjust the microwave signal here to adjust the flux offset between two lasers. So at the beginning of the experiment, we have to adjust the frequency offset to make the two lasers to be the same. But the problem is that the cavity will be affected by the temperature, so there will be a drift, linear drift. In our laser, it's very likely that the drift direction is the same. So the respected drift rate is almost 70 millihertz per second, and it will be 1,500 hertz per day. We also test our laser with the Jilan Institute of Quantum Technologies laser, ultra laser, and maybe we drift in the opposite direction, and the drift rate will be 2 kilohertz per hour, so it's very fast. Fortunately, we use the optical focus feedback to calibrate their drift rate. The x-axis, we can see this picture A, B, C. The x-axis is the compensation signal. It will be very sharp in the shorter fiber because the flux offset is it will dominate the phase drift. And then we plan that on the long fiber, 650 kilometers fiber. We can see that the drift rate is broadened. It's obvious to see that because the phase drift will be negative or positive. Yeah, maybe, but it's interesting to find that the average of this compensation signal is will match the flux offset very well. So we can compensate the drift data mu in real time. Like this, nice. Lastly, we ran the LOPP send and not send twin field QKD protocol for several distance. We represent our experiment result in terms of cycle key rate various distance. Simulation caps is in red line and the plug bound is in black line. With finite size effects being taken into consideration, we obtain cycle key rates. They all overcome the bounds at 615 kilometers. The cycle key rate is 9.70 times above the bounds. We also explore the asymmetric case. We developed that from 22 kilometers to 1,000 kilometers. I think it's the longest asymmetric distance result. We also compare our result with the closed configuration as I introduced before. We found that there are two important factors: the x-basis qubit error rate and the z-basis qubit error rate. There is no degradation on that. So we're happy to see that our system works at last. And we just finished the failed try with this open TF-QKD system in China with the cooperation with the Jilan Institute of Quantum Technology. and but we have not finished the paper. Maybe we can introduce this result maybe in next year. After the OpenTF-QKD, we are thinking about what's the next development. Shall we remove all the face tracking module in the system? And the answer is yes, thanks to the new protocol. Professor Mara from Tsinghua University has introduced the modern Parry QKD in details in yesterday's tutorial. I think most of people here should have much knowledge about that. To resolve twin-filed QKD's shortcoming but maintain the long-distance advantage, two independent terms propose a simple MDI QKD that realize repeat communication through post-measurement coincidence pairing. This figure shows the basic idea. In generic MDI QKD, Alice and Bob send photons to Charlie to make interference, and their channel transmittance is square eta. In the conventional MDI QKD scheme, only two photons arrive in adjacent time window can be paired to form a successful coincidence, and therefore the key rate is proportional to eta. In the new protocol, Charlie can parry arbitrary to photon detection events as long as the temporary separation is less than the mutual coherence of the Alice and Bob's laser. We also make a strong limitation to decrease the qubit error rate in the X basis. The interval, the delta T is the parry interval should be less than TC. So the phase drift will be not so much, and the qubit error rate will be not so much. Thereby, this new protocol improves the parry success probability, and the cycle key rate can be proportional to the square eta. I think it's a very good idea, yeah, to make the system simpler. This table shows the comparison between different measures. We can see that the OpenTF-QKD cannot remove the face tracking module or the bright reference light. And the MNDI QKD cannot beat the cycle key rate, the protocol bound. But the arbitrary MNDI QKD or the modern Parry QKD can gain all the good characters. We have to point out that recently there are 3 papers to make the system simpler with different technology. Two group, the first one and the second one, demonstrated the post-measurement Parry QKD protocol. The first one is from Jianwei Pan's group. They employ conventional lasers with a narrow linear width. The bright reference pulse are used to estimate the wavelength difference between the two lasers. They use the maximum likelihood technology to estimate the flux difference. The second one is our experimental result. The most important thing is we should make the frequency alignment begin the system setup and compensate the frequency drift during the experiment. The third one is also from Jianwei Pan's group. They applied a simpler phase estimate and tracking mechanisms with brighter reference pulse to a TF-QKD setup. They use the FFT-based algorithm. I think it's a kind of algorithm in the classical communication, because usually we will analyze the time domain to the flux domain. In the following, I will introduce our work in details. This figure shows our system structure. The laser source is the ultra-stable laser with sub-Hertz bandwidth, and the UM in the PDH locking will make us can control the flux offset very good. The encoding is running in 1 GHz repetition rate. There is no any reference line here and no need for phase tracking. So is different from my first work. The effective QKD network is effective QKD clock rate is just 500 megahertz. Now it's 100% duty cycle for the quantum clock rate. Then the SPD has the following efficiency and the dark counts rate. This picture is very interesting. Yeah, we make a lot of efforts to extract that. In order to verify the synchronize to photon interference, we first do a very simple experiment. We make the frequency offset as 5 gigahertz, and then we modulate the pulse one by one with 0 and pi in the short fiber. Then we use the post measurement Parry scheme to get the coincidence pair, and we are happy to find that it's a very beautiful curves like this, and the pair rate match the flux difference very well, and we transfer that to the x-basis qubit error rate, and we also find that there's a pair rate match this flux offset very well. For example, the red line shows that 5 gigahertz flux offset correspond to 200 microsecond pair rate. The effect by fiber fluctuation and flux offset on the asynchronous to photon interference can be theoretically derived as this equation. V2 is their visibility. Sigma is their standard deviation of the phase drift rate. Delta F is their flux offset. Delta T is their Parry interval between two time beings. And it's interesting to find that in the 201 kilometers fiber, we ran this protocol, and we found that this pair rate also drift match this flux offset very well. But we find that with the effect of the fiber, it will be a damp amplitude with the increase of this the interval, and this minima is bound by the green line. This green line, the flux offset is almost 0. So this picture is very interesting. And this picture also shows much information here. The x qubit error rate increase faster for longer fibers. Because the longer fiber, the faster phase evolution, and finally the qubit error rate will increase to 50% because the phase will be random after a long Parry interview. You don't know he will go to the detect 0 and detect 1 after a very long time the drifter. At the maximum length of 508 kilometers, the x qubit error rate reached almost 30% at a time interval of about 100 microsecond. However, the actual average interval is much smaller because our scheme pair just 8 giant photon clicks. We list the average pairing interval at various quantum link fiber length here, and we are happy to see that although the pairing interval, the value we set is 200 microsecond for the 500 kilometers, but the average Parry time is just 70 microsecond because we chose the adjunct Parry strategy as the Professor Ma introduced yesterday. With the I have to emphasize that the short Parry interval leads to low qubit error rate in X basis, but we should make enough Parry interval to get enough counts in the effective duration, especially for the longer fiber with high loss, because if there is so many loss, and it will be difficult to get the parity counts in a shorter interval. It's a trade-off between the parity counts and the qubit error rate. The figure 4 presents our experimental results. This is in red counts. Together with the theoretical simulation, over 508 kilometers fiber, our system can deliver a finite-size cycle key rate of 42 bits per second, beat the protocol bounds. I think this is the first time that we can beat the protocol bounds without the global phase tracking. Significantly, the cycle key rate at 306 kilometers can exceed 5 kilobits per second and meets the requirement for leave one-time part encryption of voice communication. This picture shows our key rate comparison with the existing result, and we are happy to see that the MNDI QKD with post measurement parity scheme offer repeat-like rate loss scaling, but also has the advantage of not requiring global phase tracking, especially during the 200 and 500 kilometers. It can be comparable with the famous TF-QKD protocol. Let us finally make a key rate comparison with all the results. Firstly, as I said, the TF-QKD, the TF-QKD and the modern parity or asynchronous MNDI QKD is comparable in this distance. But the system should be much simpler. So we recommend that we can use this protocol in this distance. And if the distance is less than 200 kilometers, maybe the core EB4 is a good choice. And we just gave this recommendation as this experiment result. Because in this longer distance, just twin field QKD can reach more than 600 kilometers or longer. Professor Ma said that said yesterday, maybe we can make a prioritization optimization, or there will be better parity strategies so that we can also push the synchronized MNDI or modern parity QKD to a longer distance. I'm happy to see maybe we can do that result in the future. In summary, we developed a first open twin field QKD setup and confirm the repeat-like behavior at a distance of 650 kilometers. We first introduced the open channel stabilization technique with coherence flux comp to compensate the phase and the laser frequency simultaneously. We demonstrate the synchronized MNDI QKD, also the modern parity QKD, overcoming the protocol bound without the global phase tracking. The removal of phase tracking ensure an economical and efficient intercity quantum signal network. In the future, we expected to increase the clock rate, and we can also use the demanding laser for the practical enhancement. I also introduced the fast count rate APD in our group. Is a good fabricated device, and it should be useful in the future. All this technology or device or experimental design, I think should be useful for other technologies. For example, the DLCZ scheme with a single photon interference, and the sensing the vibration with the interference result. They also have the similar requirement. Thanks very much for the team members in our group, and thanks for the cooperation with Nanjing University. This is the photo of our group, and Zhi Liangyuan is our group leader. He transferred I think he is an expert in the quantum key distribution, and he transferred to Beijing Academy of Quantum Science in 2021. And this is a link of our website, and we hope maybe in the future the experts can visit our group, and maybe some people have interest in that also can contact with us. Yeah, thank you very much.
Are there any questions?
So thank you for a nice talk. Just regarding your high count rate APDs, could you develop a bit further or explain how you achieve this, or for the fabrication, or just in general about the detectors? I think you had a slide in the beginning. I was just quite curious.
You mean which one? This one?
No, it was even further in the beginning when you cited, I guess, the paper. I don't know, but can you maybe give a comment on them?
Oh, your detectors. Oh, okay,
sorry,
okay.
yeah.
You mean this one?
Exactly, yeah.
Okay. I think it's similar as the it's the Toshiba detector in the maybe 10 years ago, but we use the ultra narrow interference circuit. This was with this circuit we can improve the signal to noise ratio, so we can get the signal from the small signal from the APD very well, and we also use the very high gating rate. Yeah, so with I think it's a kind of it's kind of compilation of the faster speed circuit and the filter together. Yeah, so we can extract a very small signal from this APD. Yeah, so the count rate is very high. Yeah. If we increase the gating rate, it will be maybe more than 1 gigahertz. Thank you.
Yep. Hi. Thank you for your talk. Could you comment on the expected performance if you had the fibers going over long distances between cities and having different temperatures and vibrations affecting the fibers?
I think it's fine because we just finished the field trial. We also meet a lot of problems here, but I think the polarization maybe drift a little faster than the lab, and the phase drift also similar. Yes, also similar as the fiber. So all of this. All our technologies can work in the field trial. Yeah.
Thank you.
Any other question? Maybe I have a question, actually. I was wondering, is there any intrinsic limitation of your frequency comm technique with respect to the homodyne OPLL, or you think you could reach the same distance, like, for example, 800 or the 1,000 kilometer distance?
Okay, I think the limitation is in the detector. Yeah, the next talk, the Liu Yang professor will introduce that in details, because currently the counts is maybe 2 hertz. Yes, if the distance is very longer, we cannot extract cycle key with that.
Okay, thank you very much.